Okay, this lecture is about it's called circuit pitfalls. By that it means all the second order things that could break your circuit, although you've done everything by the book. So let's think about what some of these things could be. One, we're going to talk about variations. These are variations in production, processing, supply voltage, over temperature variations, things like that. It's basically the environmental factors that you have to deal with and the manufacturing factors. We'll talk about some various noise sources, how circuits can degrade over time, and then some general shortcomings of some mostly non-combinational circuits. Combinational CMOS circuits, like we've been talking about, inverters, etc., are pretty robust. But when you talk about sequential circuits, things like that, things can break. In terms of the variations, the first topic we want to talk about is we can talk about process variations. So these are things that happen during the manufacturing of the circuit. When you manufacture anything, whether it's semiconductor circuits or screws or boards or engine parts or car doors, etc., there's some level of variation in production, especially when you're talking about potentially millions and millions of parts that you're making. So some of the main variations during the process are the threshold voltage of the NMOS and PMOS, V sub T's. If you remember, these directly were proportional into two things. Basically, really the currents of the CMOS. So the ID on and also I leakage were both dependent on this. Most of the dependence over process parameters on leakage is threshold voltage is going to be the ID on. Channel length itself is sort of a geometric effect. And you also have to remember that our main knob for changing the current was, and then it was mu Cox, and then the voltages and so on. This is for the saturation voltage. But the current is a strong function of the length. So if there's a change in this length, depending on the process, the baseline current's going to change. And then finally, the interconnections between circuits, there's, the model of an interconnect, there's a piece of metal that's the connection between circuits. And if the geometry of this piece of metal changes, it will change the resistance and the capacitance that interconnect represents. In terms of the environmental factors, the main things are that the voltage to the chip or across the chip is not going to be uniform. In fact, you might get voltage droops across the chip. This is because of the resistance of the power supply network, the grounding network. So various parts of your chip might actually see significantly different voltages. And again, that goes back to our current equations and how fast the circuits are turning on and off because of this voltage. And the other environmental effect, big one, is the temperature. As your environment changes temperature, the ambient, you could imagine your circuit being in a very cold environment or a very hot environment, depending on how the user is, where he is or she is using it, and also the power consumption of the circuit, depending on how good the system is removing that power. The temperature of the chip might vary either across the chip or of a chip itself, and the hotter the temperature, the slower it'll get. The colder the temperature, the more power consumption it'll use. And finally, the circuit itself can age, just like anything else, ages with sort of the stress, strains wear out of time. So let's first look at the process variations. The threshold voltage is coming from a distribution of dopants in the channel. So for example, here's a cross section of a device. So if I was going to draw this across, they would have, usually we see this as like N plus, N plus, and then there would be a gate oxide and a polysilicon gate. And so this would be the source, this would be the drain, this is the gate. So this is a representation of this. It's drawn much nicer in the sense that it's a three-dimensional drawing that's showing both the width and sort of along the length of the device. Usually we're like looking in this direction. So this drawing is in this direction. We're looking at a cross. And these things that I'm drawing as nice lines here are really dopant, created by dopants that are implanted into this device. And the dopants aren't going to show up uniformly, just like anything else. They're implanted, means that dopant atoms are shot into this. And so they'll have different trajectories, and each device will have its own distribution of dopants. It's like, again, it's like shooting something into this. Uh, and so each device will have a different concentration. And so there is a variation represented as the standard deviation of the dopants, the dopant uniformity, the dopant values in this channel. And it so turns out that it's really dependent on the channel area. So this channel area, the bigger this channel area, the more the possibility of the dopants variations happening here. So, but you always have some variation in dopants. So that means that even devices sitting next to each other are going to have slightly different threshold voltages. And, you know, certainly devices from chip to chip, from wafer to wafer, from wafer run to wafer run may have significantly different threshold voltages. The other thing that would systematically or can vary both randomly and systematically is the channel length of the transistors. The systematic variation across the chip is caused by the lithography process. If you guys remember back to our lecture on how these devices are made, you'll remember it was a printing process using masks. We have very sophisticated lithography machines that are printing, right, lithography. Machines that are printing these devices, these transistors on the chip. And that replication from the mask to the chip isn't perfect. And you might have and will have some systematic variations in the width of devices across the chip. This means systematic means every chip you get would have this variation. So this threshold voltage variation is kind of like random. You'll see it being different from transistor to transistor. Chip after chip will have a different distribution, sort of semi-randomly, of thresholds. The systematic means chip after chip, things on one side of the chip are going to be looking different than another side of the chip, just by the fact that the way the device was printed onto the silicon. And so one side of the chip, the channel lengths may be shorter. That would mean that the devices that are faster on one side of the chip would have longer transistors and vice versa, it'd be slower. On top of that, there are also the processing itself. There's at the very, very sort of nanometer level, there is a process roughness in the way the channels are printed. So that by itself also gives you a variation in the channel length. Finally, in terms of the interconnections, the etching of the interconnections isn't perfect. And so you will have variations in the width of the metal lines, the thickness, the height. So all sorts of things can vary, but these are the main variations. Okay, so these all kind of show themselves in various ways. And one of the main things used to be the case, but you'll see variations in these cases. So this is a plot of a wafer and the variation, the performance of a ring oscillator in the wafer. The ring oscillator basically represents how fast the devices are running. I'll be talking about that in a little bit. But um, this shows a distribution where the frequency of the ring oscillators are running much faster. So this is what's called a thermal map, meaning that the colors represent different values. Okay, and then this shows the X and Y position of those circuits on a full wafer. So this would be, I don't know if this is an 8-inch wafer or a 12-inch wafer, but you get the idea that the circuits here at the center, they're representing dark in the thermal map, and so they're running much faster. But that's just one way things can be varying. There's lots of variations, and you'll see this once you start producing these parts. So this type of variation would look like either, depending on the size of your die, the size of your chip, it would either look like a die-to-die variation or within die variation. So you can imagine if your die is rather large, so your chip would look like this on the wafer, stacked up next to each other. So inside the chip, uh, you would have like this chip here, if it gets printed, part of it would be like part of the circuits would be running slower, part of the circuits would be running faster, depending on where it's printed on this chip, on this wafer, sorry. So anyway, so depending on the size, these variations could mean you have variations inside the chip. So that means, like, I don't know, one flip-flop in one corner of the chip will have a different setup and hold time than another flip-flop in another corner of the chip. Then there's the die-to-die variations, meaning one chip you get could be running at, you could run the clock as fast as 3 gigahertz, and then you'll get another chip on the same wafer that the clock would be running significantly less. So for example, imagine a chip is made here versus a chip over here. This chip down here in the center is going to be could run much faster than this. You see this sometimes when you see different grades of microprocessor parts. So you'll see, some clock, they're selling something that can run at 3 gigahertz for more than something that runs at 2.8 gigahertz. Those are all coming from the probably same wafers. They're just getting cherry picked or binned in the language of the business, so that you're separating slow from fast circuits. The same thing could happen from between wafers. So even in the same run, in the same process run, each run is either 12 or 24 wafers. Some of the wafers could be different than other ones. I had was talking to a person with a lot of experience in production, and he would always be looking for possible variations in the first and last wafer of the lot. So let's say you got a 24 wafer lot. So the first and the 24th wafer could be very different. Another weird thing we saw one time in a production run, which was very interesting, is we saw a variation between even and odd wafers, and that took us some while to figure out that at some point in the process, the odd wafers would go to one machine to get processed. Basically, at that point in the process, they would have two machines in line working in parallel. So all the odd wafers would go to one, and all the even wafers would go to another, and then they would get recombined again in the same lot further on down. But that would actually created this even odd effect in the process, which was kind of interesting. And then different wafer lots, as you can imagine, if you process a set of wafers today compared to a set of wafers 6 months from now, things might have changed at the at the factory. It could be that the calibration values of the manufacturing parts have changed. Just processes tend to drift over time, and a big part of what the manufacturing engineers do is to try to keep them on track or bring them back to the baseline. But each time you do a run, things could be different. Generally, you could say that closer transistors, meaning transistors that are physically closer to each other, match better. It's that's I would say that's a true point. I think you're getting rid of a lot of these variations with this physically closer transistors being better matches, and also being mirrored or having exactly the same shape is very important. But I think that's you could say that's true. There's of course there's still some variations even the close transistors. Okay, so that was all the process variations. Then there are also environmental variations, the big ones being voltage and temperature. So the supply voltage of a chip is spec'd to be, at a certain power supply. It might be 800 millivolts, 1 volt, 1.1 volt. Depends on the process you're running. It could be as much as 3.3 volts for extremely old processes. So that's usually spec'd at plus or minus 10%. But for sure, so when you're um, having a change of plus and minus 10% um, in your supply, remember that VDD corresponds to gate source voltage. And if I draw, for example, the saturation current of a an NMOS transistor, if I say VGS minus VT squared, the current, as you can tell, is very dependent on its VGS or VDD. So this is equal to VDD in a CMOS logic transistor. So you can imagine if I have a plus minus 10% variation, my VDD, the highest VDD compared to the lowest VDD might be as much as 20% different. And that would give me a significantly different current. So in those transistors, meaning it's significantly different speed of operation. But that variation is allowed, so you always have to design your circuits to be able to live with this level of variation. That's just expected. But on top of that, there's also the possible that, when you're manufacturing a bunch of these things on a board, that the voltage regulators on the board themselves are going to there's some variation in those. By error, I think this means variation. So just a voltage regulator that you would buy to power your chip by could have a significant variation. So some chips on some boards may be getting higher voltages than some other chips on some other boards, and they're going to be acting differently. So that's an environmental difference. The other thing is the circuits on the chip themselves could be seeing different voltages. Here's an interesting plot. So I got to thank IBM for coming up with these really cool plots, which shows the sort of the position on the chip and the variation in the supply voltage at different points. And you can see some parts of the circuit, some big parts of the circuit are getting higher voltages. Some big parts of the circuit are getting lower voltages. And then there are like significant droops in some local places. And the reason for that is probably either the metal routing to these areas wasn't so great, or there's a lot of switching current. There's a lot of circuit activity happening there. Anyway, there's sort of a mismatch between the resistance of the power network compared to how much current was needed in this area. So locally in this area, um, these circuits here are getting significantly lower supply voltage, meaning that they'll be operating much slower than circuits say in this area of the chip. And so the temperature of the chip also affects the speed and power consumption, etc., of the chip significantly. This is caused by a couple of things. One of the big ones is just the ambient temperature. Ambient means the temperature in the room or the environment. So again, you could imagine if your cell phone is sitting on a dashboard uh, in Cal Poly while you're taking a summer class at 3 p.m., that that chip is going to get really hot inside. Versus, I guess there's not really that many cold places. Let's say you've gone snowboarding or something, and the same thing that you've left your cell phone, you've forgotten it in the car overnight, you get there in the morning, called it car is cold. I'm trying to like just give some frame of reference for the coldest that we probably people in Southern California probably like experienced. So there could be, and you'd expect your cell phone to work in either one of those cases. And of course, we get annoyed sometimes. The cell phone tells us it's running too hot and it can't work, but it's because of that. It's gone past that point. So that's for a commercial type application. So cell phone would have these kind of commercial specifications, and usually that's given. This is the ambient temperature, 0 degrees Celsius. Uh, so 0 degrees Celsius is when water freezes to 70 degrees Celsius. That's pretty typical. Then there's industrial products. So these are chips that or parts that you will sell into places. Industrial usually means it's in a manufacturing kind of environment where maybe it's not very well temperature controlled, so it could be a very hot or very cold factory or piece of mechanical equipment. So that would be an industrial grade part that has it could get the part could get much colder or hotter. And finally, in military applications, or the most stringent, where you could get very cold or very hot. As you can imagine, this chip sitting at minus 55 degrees or plus 125. So that's uh, the ambient temperature issues. Um, then the chip itself has its own power consumption that heats it up. We talked about that. We talked about packaging. We talked about thermal resistance. And the thermal resistance across the die and the package aren't going to be the same. Just things vary. So this is an actual thermal map of a chip in operation. And what it shows is that there are, I don't know if, let's see, what does it say? I can't quite tell. I think it looks like the darker areas are hotter, potentially, but maybe these parts are running much hotter than these areas over here. So these are like, you can actually do this with a like a thermal camera. You can look at the chip and see where the temperature profile is. And this is pretty typical where parts of the chip are going to be hotter, whether the thermal resistance to those parts is higher, there's more activity in those areas, so there's more power consumption locally in those areas, but those areas run hotter, which means that those circuits are going to slow down more. So those are the environmental effects. Okay. On top of that, there's stuff ages, whether it's mechanical, electrical, etc., but things wear out over time. And there are various things that happen. So, for example, there are things called hot carriers. These carriers are electrons or holes, and by hot, it means they're very energetic. So, if you have electrons or holes that get too much electric field, they tend to sort of implant themselves into transistor gates and change their threshold voltage. Similar things happen with the with running things at like a hot temperature for a long time, and and it also shifts the threshold voltage semi-permanently. And then there's just the dielectric breakdown of gates, etc., that just comes with time. So all these things could cause changes in threshold voltage. All right, so we'll get back to those in a little bit. But let's look at the process variations and what a designer typically does to deal with those. So just because the process is going to vary uh, doesn't mean that we can't build parts in that process. It just puts a more puts the onus on the chip designers to make sure that with the variations that are allowed in the manufacturer, you can still produce parts, millions of parts. So another way to say this is the manufacturer will do its best to reduce the variations in its processing, but after some point, it can't do any better, or it gets very, very expensive to do any better. At that point, what the manufacturer does is it measures the variations in its process and then tells the designers these are what you should expect for variations in this process. And what you should do, or what a designer will do, is then simulate or design their circuits so that they can live with these variations. So the way this is kind of represented in the digital space, this is more digital than analog, but anyway, it's a digital class, so we can focus on that. They talk about process corners, meaning places where the transistors are running faster, slower, or typically. So for example, you have two types of transistors. You have the NMOS transistor and the PMOS transistor. It's very possible that the NMOS transistors are going to be running faster than the PMOS in certain place, in sort of certain wafers, and vice versa. So the way basically you see a plot of NMOS versus PMOS, NMOS slow, NMOS fast, PMOS slow, PMOS fast, and all these corners, so-called, are manufacturing permissible corners. So it could be, this means that both the N and the PMOS FETs are running slow, and MOSFETs are running fast, PMOS is running slow, and you get the idea. And typical is what's sort of in the center. And the way it really typically looks, or the way it usually is that there's a if you actually look at the distribution of the wafers where they fall in these values, the great majority are going to be around the typical, and there, as usual, there's probably a Gaussian distribution where that's where typical is defined, and slow and the fast, etc., are on the edges of that distribution. But basically, you have to simulate your circuit at all these points in the permitted variation of the process. So the slow and the fast define how fast or slow the circuits are, the NMOS and PMOS speeds, but there's also variations in temperature that you also have to simulate, or supply voltage that you simulate. And because they have the effect of speeding up or slowing down the circuit, they're also characterized as fast or slow. So here are some factors that you have to simulate. So there's obviously NMOS and PMOS speeds. Then there is the supply voltage. So a fast supply voltage is defined as a high supply voltage. So this is for a 1.8 volt process. And at a 1.8 volt process, plus 10% gives you 1.98 volts, minus 10% gives you 1.62 volts. Both of these are permissible for the chip to run at, or for the transistors to run at. A 1.89 volt device will be running fast, and a 1.62 volt device, in terms of the VDD supplied to it, is running slow, and a 1.8 volt device is running typical. So you have to simulate with all these voltages when you're simulating. So for example, I'll give you an example. When you're simulating a slow corner, you'll be using the slow transistor model. So the foundry actually gives you those models that represents the slow transistors. But on top of that, you're going to be running your circuits with a 1.62 volt supply. Correspondingly, in the fast corner, you'll be using the fast models from the foundry, and you'll be simulating that with a 1.98 volt supply, because that's the fastest possible circuit running that way. Temperature is defined the same way. Typically fast, this is for sort of across the possible junction. This is the junction temperature. So in SPICE, there's a dot temp card or line in SPICE, dot temp, and you basically can adjust your temperature with that. This is the junction temperature, or the actual device temperature. So when you're doing this fast simulation, again, you're doing the fast NMOS, PMOS models at the high supply voltage, but you're also going to run them at a very low temperature, so at 0 degrees temperature. And the slow will be with the slow models, 1.6 minus 10% VDD and a hot temperature. So this is how you'll be simulating these. And then basically you have a checklist of different things that you're simulating with various, sorry, I didn't mention wires. Wire will have its own variations of fast and slow. So slow wires would be, for example, probably end up being over-etched or thinner wires, so have more resistance possibly, things like that. But they'll be provided from the foundry models for that. So this is like the checklist of the simulations you'll be running. So this, when you're designing a part, you're not just doing typical simulation at one temperature at what supply, but depending on what you're checking for, like worst case performance, you might be picking different values. For example, if you want to see how fast the parts are going to be running, these are like good parts that like typically good ones will have like typical transistors, typical supply, typical wire. Sorry, slow supply, slow temperature, because that's the worst case the customer can do to your chip. If you want to be really conservative from a timing specs, you're going to be also simulating your circuit components in the slow domain. Things like hold time constraints, race conditions, etc. They are worse when circuits are running fast. So you'll be simulating those to see where the problems are in fast conditions, and so on and so forth. So depending on what you're checking for, you'll be using a different set of simulation um, uh, models. So there's the models, so these are the process models, and this would be the supply and the temperature. So the these corners are modeling the device as if all the devices in your circuit are going to be sort of have slow N MOSFETs, and all the devices are going to have slow P MOSFETs. But because of the variation, the random variations in manufacturing, it's also possible that in the same circuits, some of the N MOSFETs are going to be running slower than other N MOSFETs or P MOSFETs, etc. So Monte Carlo, what the Monte Carlo simulation does is it looks at this variation, this possible variation across the device, so you can basically see what happens when you randomly things vary, which as opposed to all the device running in the same direction. Okay, so those are the variations. Let's look at the noise. So again, this is assuming you've done everything correctly. There's still the noise, various noise sources in the chip itself and then in the environment. For example, the power supply can vary quite a bit. We've talked about that because of the inductance of the wire bonds. You try to do what you can with decoupling capacitors, but it may not be sufficient, or anyway, it works to a certain extent, and your chips have to work within those bounds. And so the power supply could have a noise, ground could be going up and down. You could be getting capacitive coupling between signals typically happens along long wires. If you get capacitors, if you got dynamic circuits, you could get charge sharing, you could get leakage, which could change the value of some dynamic latches, etc. So there's lots of sources of noise. By the way, there's two kinds of noise. So in the analog domain, you might run across thermal noise or 1 over F noise. These are device level statistical noise variations. This particular noise that we talk about and the noise that's more important in digital circuits are these sort of environmental noise sources like these guys that we're talking about. Anyway, the consequences of those noise are either increased delay, so as voltage supplies droop, etc., things might take longer to settle into the correct value, and you'd have to wait for things to settle to the value before the clock edge can sample them, which means a delay. Or what's worse is incorrect computation, which would be a really bad situation. Okay, so those are the noise sources. In terms of the reliability, this means that when you're building a chip, you're selling it to somebody, your customer is expecting that chip to work in that part for a while. And it's possible that because of the design, manufacturing, etc., the chip wears out um, earlier. So that's sort of the hard wear out issues, etc. So we'll talk about that. And in fact, what you'll see over time, so if we plot the time versus the failure rate of devices, what you'll see is they call it this kind of this tub curve. So there are some devices that fail right away, and some devices that wear out, and then the vast majority of parts, if that are manufactured properly, are going to be sort of in this range. And you want to make sure that this range is long enough to match what your customer is expecting. On top of that, there's also soft errors like things like radiation, etc., that might cause errors in the circuit. We'll talk about that a little bit, and then how to characterize these failures. Okay, so when you look at commercial parts, typically they're expected to last over 10 years. And so that's all their reliability checks that the customers and yourself will be running is trying to figure out uh, that whether they last 10 years. But the problem is you can't really test the device for 10 years because you just don't have that long amount of time. So the question is, how do you test the device over a matter of several months to see if, to get an indication of whether it'll last for 10 years or not? And the idea behind that is something called accelerated lifetime testing to see whether the part will last the 10 years. And the idea is that you will be basically running the part at both high voltage and high temperatures. So what you do is you typically select some number of parts. Depends on the reliability date, sort of the reliability or qualification requirements that you're following. But it might be a couple of hundred parts from different manufacturing lots. And you take those to a reliability lab and you basically put them in a oven. So, and that basically you're just running the parts constantly at higher voltages for an extended period of time at the elevated temperature and seeing if they'll break down. And that's elevated temperature and elevated supply voltage. They are sort of doing a premature aging of those parts so that, again, in a matter of few months, you can see, sort of simulate the effects of the part operating normally in 10 years. Okay, so the different ways that the part can fail are, one of them is just hot carriers, is that high electric fields can make electrons or holes very energetic. So these high energy carriers are called hot, and they're actually going to embed themselves into the gate oxide, or they can embed themselves into the gate oxide and get trapped over there. And if this happens enough times, they actually can shift the threshold voltage over time. And eventually the threshold voltage gets high enough that the circuit slows down and stops working. Depending on which way it goes, it could either the threshold voltage goes up or the threshold voltage goes down. Neither one of them are great. As you guys remember, high threshold voltage reduces the uh, speed. Low threshold voltage increases the leakage current, and either one of those could be bad, especially if you weren't planning for them. So what happens there is the manufacturer basically has already chosen the supply voltage to give you a reasonable product lifetime. So that's where the 1.1 volt plus minus 10% or 800 millivolts plus minus 10% comes from. The manufacturer has done the tests and tried to make sure that that all the devices get a reasonable lifetime over that time. But going back to, for example, we had a really nice plot of, like, for example, the variations in supply voltage across the chip. You can see that some circuits might get a higher or lower voltage than sort of the nominal or expected. So your design may be contributing to over voltage in some parts. So, okay, so um, the other issue that is actually, even with the supply voltage being correct, over, or if the device is in temperature for a long time, has elevated temperature for a long time, a electric field across an oxide can be causing that oxide to change by itself. So the oxide is the gate of your devices. Um, so this oxide, especially the silicon dioxide interface, that's right at the channel of the device. So if you draw the channel, this is the oxide. So right at that interface here between silicon, so this is silicon dioxide, this is silicon. So right at that interface, there are invariably these what are called dangling ponds. On one side, you have silicon dioxide that has some bonds, certain number of valence bonds it can have, and on one side you have silicon, which can have a certain number of valence bonds. And since those aren't matched, some bonds are going to be dangling in between, which will be trapping electrons or holes that come by. And they basically, the temperature and the electric field can increase the number of those traps, and that can cause a change in the threshold voltage. And this is something, actually, we ran into this problem for a product at some point for a touchpad, surprisingly enough. But it it's more prevalent for PMOS devices, and sort of something to watch out for. Before we actually ran into that problem, I was worrying about that very much. So, okay, so then the another cause of failure is the time-dependent dielectric breakdown, which is when just a stress across the gate oxide increases over time and sort of increases the gate leakage. And that increases also with temperature. Nothing seems to like high temperature much. And so just the electric field can break down the dielectric by itself. Okay, so that was the MOS transistors. Then there is a way that metal lines can themselves break down. So these are the interconnection between the transistors. And this is called electromigration, which is a very interesting effect. Is that if you run too much current through a very tiny wire, you got to remember these are really, really small wires. The large number of electrons going through can actually start removing atoms of, let's say it's aluminum or copper, removing those atoms um, of the wire and putting them somewhere else. So at some point, this actually wears out the wire and causes a blockage. So like a really disturbing analogy, maybe like could think about if you have too much cholesterol in your veins or in your arteries, that can cause sort of like clogging. This is kind of an opposite effect, but you get the feeling is like you get too much of some fluid. In this case, it's kind of like you can imagine that electron current being a fluid type of analogy can actually affect the tubing itself. So this can cause open circuits, and you really have to watch out about how much current you run through a certain width of a wire. This is a real issue and something to really watch out for. Putting when you're doing building your devices, if you run too much current through a wire, and that's typically defined as 1 to 2 milliamps per micron squared of wire cross section, and you could run into a problem. So there's some these videos unfortunately aren't working, but there's some really cool electromigration videos. If you look for that in YouTube, I think you're going to see some really cool videos, sort of like speeded up videos, seeing how the metal lines will degrade. Kind of interesting. I haven't seen this particularly, but it's possible that also if you run too much current through a wire, it would heat and sort of make the wires more resistive. I can't say I've really like run into this. I think you'd just because that um, uh, I think you try to make your devices a little bit bigger, or your wires a little bit wider, just for electromigration. So I'm not sure I've really ever seen this thing. Um, okay, so then so those were like breakdown effects over some amount of time. It's also possible that like a momentary over voltage situation can damage transistors. So again, you got to remember these are very, very small transistors, and it doesn't take a lot of voltage to create an electric field, because you got to remember electric field is voltage over distance. And when you're talking about very tiny transistors, this distance is very, very short. Anywhere on a transistor, distances are in nanometers. So even small, like you don't need like thousands of volts to damage a gate oxide. 3 volts may be enough to affect uh, a thin dielectric. So we talked about ESD, or electrostatic discharge, earlier. This is like could be a very large voltage. So this is where you might actually see thousands of volts. So is this possible? Those are usually happening at the periphery of the device, so at the pins, etc. If there's improper handling or improper electrostatic discharge protection circuitry on the chip. And then again, oxide voltages can break down even at voltages that don't seem particularly high. But again, because of the small, really, really short distances in transistors, that the breakdown can happen, um, uh, even at 3 volts or less, depending on the process. And then finally, the source and drain can permanently short, punch through together, and so there's electric fields, or like can even momentary high electric fields can affect your devices. Latch up, I haven't seen this effect. This is just something maybe it's good for you guys to know. I'll go over it really quickly, but um, again, I haven't seen latch up in any, thank God, on any of the projects that I've worked on. The idea behind the latch up is just because of the nature of having an NMOS and a PMOS in the same substrate. If you look at you're creating some unintentional bipolar transistors. You're creating a PNP from the sort of the source of the PMOS. That's the P, N being the well of the PMOS, and then the other P being the substrate. And then there's an NPN, which is the N of the well, P of the substrate, and N of the NMOS source. And then a couple of resistors which come from the resistance of the substrate and resistance of the well. And so these are unintentional parasitic circuits. And so if you draw those, you end up with a circuit like this. And this circuit, if it's given the wrong pulse, I forget which way the pulse has to come in, but this thing can go into a positive feedback loop and cause this thing called a latch up. Basically, it sort of gets a very high current through these devices and prevents them from working. So the circuit so-called latches up. Again, I think if you're careful in the design in your main circuits, you don't really see them very much. This is sort of something that had happened in the past. These days, you see them more possibly in the peripheral circuitry, in the I/O pads themselves, and really the way to get around these, I think you might have seen it in the I/O when we were talking about input-output pad discussions, where we had guard rings placed around the P and the NMOS to prevent this from happening. So those are those permanent errors. Then there are something called soft errors. They're called soft because what happens is the error comes, it disturbs the circuit operation, but it doesn't really affect, if you sort of restart the chip, it'll restart okay. It's just that bit got flipped. And really, mostly it's kind of a radiation effect. I I don't think you really need to worry unless you're like a random access memory designer, etc. You don't have to worry about these things sort of in commercial or industrial parts. If you're designing parts, when designing for parts for space or high altitude flying, etc., there's a lot more radiation in space. So there, you have to do take lots of precautions with your circuits to make sure that these soft errors, these are like, it might be individual alpha particles or cosmic ray neutrons that would flip, say, the bit value of a flip-flop or a memory. So you have to do things like voting or like hardening your circuit for radiation. But I don't think we need to really get into that. It's pretty specific. Anyway, that's the lecture, but the problem with these failures is that a lot of times they are, when they happen, it's hard to immediately narrow down the cause and where it's happening. Because imagine if you could have a failure somewhere in your chip, not every point in your chip is observable from an external standpoint. And so there's a lot of detective work that's needed once these things happen to get to the bottom of what happened. And, the best way, of course, to deal with them is to take the required precautions to try to prevent them from happening. It's not always possible that those will prevent things from happening, but that's your best bet. Because once they do happen, then uh, it's a real effort to narrow down the cause.